And anyway, I would rather have a discussion. We don't have an official discussion today, but I'd rather have a discussion now as well, because I have a lot to talk about. So again, all kinds of questions are welcome. So at least, I want that after the end of the talk, we at least can, this is my usual goal, decipher what the title stands for, or we can do this substitution in your mind, but we want to get more to that. So I guess this whole line of work that we're pursuing here, which is kind of in line of the workshop, is what are the necessary and sufficient complex theoretic assumptions for cryptography? This is like a very, very broad question, but this question actually has limitations because we have to ask it in the right way. What do I mean by that? So imagine that I'm going to have a conversation with a cryptographer. So say Russell, I mean, you're an author, but suppose you're making a copy of Russell and having a conversation. So the problem is that this conversation is going to end pretty fast. Why? Because on one hand, in complexity theory, one of our holy grails is proving explicit circuit lower bounds. Yet at the same time, essentially everything that the cryptographer is going to tell you, any basic thing, any basic cryptographic primitive already implies circuit lower bounds. If this is what we want to do, we can end this and go outside and enjoy the wisdom, because that's it. So just maybe to give you a few examples, the first thing that the cryptographer might say, one-way function exists. That's it. We kind of get it. Okay, even if you want to be more specific, the one-way function which is secure against p/poly, then let's say you separate p empty from p/poly, you separate p from empty, you separate everything from everything, our job is done here. Right, so and you can kind of iterate it over other interesting things like computational zero knowledge and etc. So in order to have any meaningful conversation, we should at least start by asking, okay, are there any cryptographic primitives that do not imply those lower bounds, at least not immediately? And well, there happen to be a few, and they heard about them, but I'm going to introduce one. And one such primitive is obfuscation. So what's the deal with obfuscation? We already heard about it before, but let me try to reiterate. The idea is basically you're taking a program and you want to transform it into something which is unintelligible, something you cannot recognize while preserving the functionality. So I know that nowadays it's very common to teach Python, but I'm old school, C++. So here is a C++ program. So this is a valid C++ program. If you take any standard C++, even like Visual Studio C that I used to work with, run it, it will compile with 0 errors, it will run, it's a valid C++ program, okay? For those of you who don't know the answer, what does this program do?
And stores them in integers.
It looks like you already, you know C++ better than me, I guess. So that's indeed the case. So if you take this code, this one-line code in C++ and you obfuscate it, you'll get this. So this is an equivalent code in C++, so that's exactly the same thing, right? So that's what we're talking about. So this idea gives rise to the notion of I/O or indistinguishability obfuscator, which basically kind of tries to get towards that kind of an ability. You can think about this I/O as a kind of a compiler, right? You take a circuit and you compile it, you obfuscate it. And the goal is that if you start with two circuits of the same size and the same functionality, if you look at the obfuscated circuits, you cannot tell them apart. Basically, they are indistinguishable. The obfuscation of C1 is indistinguishable obfuscation of C2. Right, I'll be more technical in a bit, but this is sort of what we want to do. Question? Thank you. So what do we know about I/O? So we already heard a few things about it, but I/O turns out to be very instrumental in various constructions in cryptography and complexity theory, things like deniable encryptions, multi-party computation, finding Nash equilibrium, etc. And on the bright side, the last 15 years or so, we've seen a glory of culminating construction, chemical construction, culminating in the recent work by GLS, which basically allows you to get an I/O the way that you want it, based on 4 assumptions now down to 3 assumptions. So it's all good, but kind of going back to the original question, what are the exact conditions for the existence of I/O? And let me just say that unlike the vast majority of cryptographic primitive, this is a little bit tricky. Why is that? Because everything, one-way functions, pseudo-random generators, all of those things basically cease to exist if P equals NP. They just don't exist. On the other hand, I/O does exist. In fact, not only it exists, you get like a bulletproof I/O. What do I mean by that? So you can think about the following procedure. You take a circuit and you output some kind of a canonical representation, say the first lexicographic is smallest equivalent. So this is something you can do unconditionally in sigma to second level of the polynomial hierarchy. Of course, not going to be efficient, but if P equals NP, you can do it in polynomial time. So again, not only that you don't have I/O, P equals NP, you get this bulletproof, this super powerful I/O. So this is sort of the key difference between I/O and maybe other cryptographic objects that we can do it. So this kind of brings us to the next question: where could such an I/O live?
So just to make sure I understand, it's not the case that I know could exist, I know would exist.
Yes, you actually get it. That's the same. You actually get it. What you're going to do is to take a circuit and it's like the circuit equivalent circuit minimization problem. You can think about it. So again, you can do it unconditionally in sigma 2. This is actually complete for sigma 2. But if you want to be efficient, you cannot do it. But if P equals NP, the whole hierarchy collapses, you can do it in P. Right. So again, not only it could exist, it would exist. It will exist actually. With more questions.
I think this is the definition of I/O, but you could just have I/O be the constant circuit 0 or something like that.
So
I mean, you want to do the same function.
so I didn't. So I didn't give you the full definition, but that's, I mean, once I give it, that's not going to fly.
Okay.
More questions? Michael?
What if like just search MCSP is in there? You get it or no?
Search MCSP. Search MCSP. So it's slightly a little bit a different problem. Why? Because in the MCSP, you get the whole truth table. Here, you don't get the whole truth table, you get it in the circuit encoding. So it's not clear like how you overcome this. Like you'll have to find a way to stretch it and compress it on the fly. I mean, compressing it, you have the search MCSP, okay, I have to find a way to sort of stretch it and compress it on the fly, which I don't know how to do. Then we can talk about the software, I don't know how to do that. Good, more questions? So again, where does NIO live? So it kind of, it's a,
So you just.
then what was the question again?
Is if you could actually solve the minimum circuit size problem, given a circuit find electrographically first, then you could solve satisfiability, because if the circuit's unsatisfiable, the size is 0.
So yes, if you can solve
so-
an NP complete problem, then yes.
Yeah, so this is like if and only, but this particular way of obfuscating, if and only.
Well, I just meant that because C1, IO C1 would be
Yeah.
the same as IO C2 in your idea there. But you didn't say in your definition has to be the same function.
No, they have to, oh, one second.
C1 and C2 do, but
C2.
IOC1 should be the same. thing.
Yes, so I deliberately being like, this is why there's a informal sign here, because I'll be more formal later. So that's a very good question, but I'm deliberately being informal. At this moment, I will be more formal in a few slides. So yes, you can just, for what you want, you can just have a functional output file. Except it wouldn't work for other reasons. Like you can't get the deniable encryption with the function, but you can get other things. Yes, good comments. Questions? So again, where do all of us live, kind of speaking globally, specifically here, it's a good place to talk about it. So as we all know, we live in one of Russell's worlds, right? So one of Impaliato's worlds, and let's go over them and see that I/O cannot exist in all of them. So let's start with the basic one, which is algorithmic, because we just talked about, it's like P equals MPO and P's and VPP. So that's the place that I/O can thrive very well because we get the ultimate I/O as we just discussed. The next one in line is heuristica. So I guess I don't have to define it, but let's still go over this. You have NP in the worst case, but not on average, is on average in particular that excludes one-way functions. And now what happens if you have I/O, but you have one-way functions? If you, some previous results, that kind of means that NP is, there's a difference. You see, there's a capital I/O, there's a small I/O, that's infinitely often, so you can ignore it. So NP is an IOPPP essentially, which is in contrast to what heuristic does. In heuristic, NP should be hard in worst case, so this is not going to work. Similar on passive end, in passive end is a different setup, but the upshot is you don't have one function in passive end either, so the same argument works. Again, you cannot have NIO for the exact same reason. And then I guess start stepping into somewhat, I guess, interesting territory. If you kind of have a conversation with the cryptographer, they're going to say, well, it's probably minicrypt or cryptomania, right? So what about minicrypt? So if a minicrypt is place, if you remember, we can have one-way function, but we don't have this full-fledged cryptography, like so we don't have one-way function, we don't have public key encryptions. At the same time, what happens if we do have I/O? So what of Sahai and Waters shows that if you have I/O and one-way function, then you have public key cryptography, which is exactly what is not supposed to happen in minicrypt. So you cannot have an I/O and minicrypt either. So what's left, and this is probably what every cryptographer is going to tell you, is that we live in cryptomania. Basically, all the cryptography as we know it is possible. And indeed, the works of GLS, that recent breakthrough, make a good argument that IOMATIS are going to mark it as a yellow. So this has been the traditional 5 words, the seminal work of Russell, and now recently there is a new trend to add sort of this artificial world number 6 called Obfuscatopia. So Obfuscatopia is basically a place when I/O exists, and now this is this artificial thing which is basically like a bridge, like you can think of an island split into 2 parts. One part of it is algorithmic, another part is cryptomania. And the problem is that I/O kind of becomes this non-trivial thing because if you want to do cryptography, we do want to live in cryptomania. At the same time, as it turns out, if you're being uncareful, not careful, you kind of find yourself on a different side of the island. So you want to be in cryptomania, but if you do something even slightly wrong, quote unquote, you find yourself an algorithmic. So Obfuscatopia kind of spans on this both of those levels. So questions about I/O besides the comment that you made. Now, of course, that wouldn't be a meta complexity talk if I did not talk about another thing, and I'm going to say what it is, but I guess you can guess what it is, and this is the second part of the title, and that's the problem, one of the problems we're trying to solve here. So I think we had a little bit of a break yesterday and the day before yesterday. Now it's time to go back and track and talk about that. So I actually don't have to talk a lot because Rahul have done a great job explaining that. That's one of the benefits of speaking, being one of the last speakers. I can say, okay, look at the previous talks or whatever. I'm still going to mention it. So just for clarity, for completeness, we're given a Boolean thing, which is a truth table, and the number S, and we would like to know, that's a decision version, whether there exists a circuit of size S that implements that function. So one sort of basic thing, and this turns out to be the only thing that we kind of know for a fact, is that MCSP is an NP. And I have to say, this is really one of the few things we kind of know for a fact. Everything will be like speculation, condition, or whatnot. And why is that? Well, a nice exercise also to understand how things work. If I want to know if a circuit exists, I'm going to guess a circuit of size S, and I'm going to spot check it against the truth table. But you're going to say, wait a minute, it's going to take 2 to the n time, but that's the mind which we have to undergo. Yes, it's fine because the input size is 2 to the n. So this is fine. And as I've said, this is essentially the only certain thing we kind of know for a fact. And besides, they have all kinds of other relationships, but let me mention it. So one interesting property or one interesting feature is that having MCSP as an oracle turns out to be quite a powerful thing. So the sequence of work starting with the natural property framework and works of Valiant and subsequent works pretty much show that you can invert any one-way function with an MCSP oracle. So in particular, that allows us to solve those hard problems like integer factorization, diffie-Hellman lattice problems, including FCP. You know what FCP is? This is your favorite cryptographic problem. So we can solve them, and that's on my. And if I was speaking in a cryptographic dialect, I shouldn't say PPT, I should say PPTM or something like that. But I'm speaking in complexity dialect. So basically, if you have a machine with an MCSP oracle randomized, you can solve all cryptography. So this may give us or gives us the idea, well, MCSP is powerful, it's a powerful thing. So how powerful is it? Is it NP-hard? So that's this is a place when we kind of run from certainty to all kinds of speculations and reductions. So what do we know about that? So if we kind of look at that in the usual sense, the usual notion of anti-completeness, right? Suppose we had the standard many to one reduction. So works by Ryan Williams and others show that this would imply a separation from X and ZPP. So what's the conclusion here? We do actually believe that X should be different from ZPP, but this has been standing out there as a long standing open problem. It means that even if it is true, we kind of have to come up with a completely new set of techniques to try to address that. So given that situation, this hanging status, it was suggested that perhaps, the certainty complete, perhaps we should try to label it as an NP intermediate. And indeed, there were connections between this and other NP intermediate problems. So something that Rahul mentioned, I'm going to mention it again. So you can solve other NP intermediate problems like life isomorphism. In fact, you can solve the whole class of SZK, which is conjectured to contain a bunch of those cryptographic problems, which is sort of this NPI, the intermediate flavor. At the same time, going back to the hardness part, all of those results still give a suggestion or suggest that perhaps it is NP-hard, but perhaps under a more broader notion of reduction. For example, ZPP reduction or BPP reductions or P2P/polar reduction, basically a reduction by arithmetic circuits. On top of that, we have a strong evidence suggested by Rahul that this is the case, and we actually heard about that. We just heard about this in this workshop that this is true relative to random oracle. So those are quite strong evidence that perhaps one of these, this one should be the case, basically. And if you want to interpret that in English, it would mean that you can take in a circuit, in a uniform circuit, you can have a circuit that contains MCSP gates, which could compute SAT, for example. Right, this is what it would mean. Again, this is the interpretation, and we think that's the case. And for those who we were here a few days ago, I was talking about that very open problem. We think that should be the case. We have a lot of evidence that should be the case, but that's still an open problem. And we still have one more day for the workshop to solve this problem. So we still have, it may not have to be open for that long. So nonetheless, cycling back from NCSP and IO, we already have some connections. So in some of the previous work, we also did establish a connection which also comes in this flavor of completeness. So suppose we have IO, whatever it may mean, then we don't get all the way to this statement, but we get something very close. We get the flavor of completeness, namely MCSP, remember, is a problem in an NP. So the flavor that we get is the following: the whole complexity, if you will, the whole hardness of the class NP kind of rests on the shoulders of MCSP. Namely, if you have an efficient algorithm for MCSP, then the whole NP class collapses to PDP. So this is kind of, again, it's not like it's a subsequent of that. It's not exactly that, but this has the same kind of a flavor. Questions, concerns, complaints? Yes?
Yes, just follow from what you said before, like event feasibility, then you can break one function and that event feasibility.
What, sorry?
Oh, so event feasibility, then you can break one functions.
Yes.
Then you can show feasibility.
So I mean, that's part of this proof. Part of this proof actually uses this result, yes, because MCSP you can break one the functions, and basically one of the things that you like the proof actually goes by essentially you invert the function which is supposed to compute SAT. Yeah, that's how it goes, yes. And more questions? Now kudos for Sam, especially for you and others who complained. Let me talk in detail about what IO is. So it's going to be a bunch of definitions, and you don't necessarily have to remember all of them, but just give the gist of it. So we do need to make it more technical, so we don't have questions like that. So especially for you, Sam and others. So what is an IO in a more technical point of view? So it's an object, a very powerful tool that was invented by seminal paper of Russell and a bunch of friends. Did you get drunk and think about it at night or something? I don't know.
It was more than one night, and we were usually sober.
Usually? So it was invented over the course of several nights by Russell and others, and there was some subsequent. So basically, what we're looking for a randomized procedure that takes a circuit and a random string and outputs from a circuit. And to make it actually useful, you do need to satisfy certain properties. And the first one is, per Sam's request, you do need the functionality property. So specifically, you want to make sure that whatever you obfuscate kind of keeps the original functionality or always. So you can think about correctness in the sense of perfect, imperfect. So you take the obfuscated circuit and you compare it with the original one, right? So if it's going to be the same all the time, it's called perfect, but you can also think about sort of an imperfect scenario, right? It's going to be the same as high probability. So many cryptographic applications actually allow that kind of imperfect, small imperfection. It will still go through. So because again, you don't have to think about parameters, think about epsilon being like really small, but just the terminology, perfect was imperfect functionality. Okay, so this is one thing. So for example, the example that you mentioned, outputting file, that's not going to work under that. Yeah, but it have to be like really, really, really imperfect for that to work. That's not the use cases here. And sort of this requirement should be balanced by another requirement, which is called security. So usually security is defined in a certain way. I want to define it a little bit more broadly because of the context. So you should think about, so Russell talked about this in the context of distinguishability, so that's exactly the case. So think about a certain class of testers, a certain class of distinguishers. So what do we want? We want the case that if we take two circuits of the same size and the same functionality, if we obfuscate them, so security against A means that this scary thing means that no distinguisher from A can tell them apart, maybe up to a small advantage, negligible advantage. Again, so usually it's not given in best generality, usually look at a particular class, but I do actually want to define it more broadly for a class of algorithms. And again, this class can be whatever you want by definition. Again, all you have to remember that security means that the circuit, the obfuscations are indistinguishable by a distinguisher from that class. And now some specific cases which are applicable in cryptography. The first case is the BPT, basically when the distinguisher is itself an efficient algorithm. So this is referred to as a computationally secure setup in the literature. And actually want to take you to the completely other end of the spectrum, which is the class of all algorithms. By all, I mean all that we want. X space complete tower of the tower function, anything essentially in R. So you can think about, well, does it even make sense? We'll talk about it, but in that case, this is called statistically secure. So I always should secure against any possible algorithm, as crazy as you want. Randomized, deterministic, doesn't matter. Sort of that end of the spectrum. So usually in a particular paper, you're going to see either this end, the low end, or the high end. The reason we need A is because they actually find something interesting in the middle of it. So again, a lot of stuff to remember, but just remember the imperfection and the security part. Questions, concerns, Sam?
So the reason it can be so statistically secure against all algorithms is because of the randomization IO, that I understand it correctly.
So that IO that you get, if P equals NP, is actually statistically secure. Yes.
Okay. Oh, I see, that one is, okay.
I mean,
But, okay, but if you say you had a one-to-one function IO, couldn't possibly be statistically secure.
no one said it has to be one-to-one.
I know you're not saying that, but if you had a one-to-one function IO, could it be statistically secure?
Probably not, because of the property, because it's one-to-one.
Yeah, because you can search through all that. Yeah, okay.
But then again, I mean, as you know, not everything has to be statistically secure. It's okay not to be statistically secure, right?
Yeah, I'm just trying to understand.
No, I mean, I agree with you, that's a very weird notion to satisfy, and actually come back to this very, very point, but as a definition, right, you do want to be secure against any possible algorithm. In particular, I mean, that puts a lot of restrictions on IO, in particular, the restriction that you mentioned, right? Questions, concerns, complaints? So now I can actually talk about some of the results given that. So,
What is your question from?
oh, but I don't see it.
What's over there?
It's not there.
I don't see it. Sorry, can you? Oh, well, I just don't
Why it's
see.
called
Oh, that might be on the, whoever's running
Zoom.
the, on the, whoever's Zoom.
Sorry, sure, Zoom chat.
What's the question again? Sorry, I didn't see it.
It's gone now.
I don't see Zoom for some reason, so, can you open the question, please?
Why is this object called an obfuscation?
Imagine an obfuscator would disguise the behavioral problem, disguises the implementation. So, I mean, the general purpose of an obfuscator is exactly to, you want to make it untellable. You want to preserve the functionality while completely sort of scrambled. So you can imagine one application is that the trademarks. You wrote some very cool code that you don't want anyone to steal. And then, you know, we can do that. But yes, why don't we let the master himself answer it?
So we didn't come up with the name obfuscation. This was a pre-existing concept in actual programmers actually had obfuscation contests where they tried to make programs as hard to understand as possible, simple function. And I'm not quite sure what the purpose was.
It still exists by the way, the competition still exists.
Yeah, so an interesting thing though, is there were a couple of academic papers on obfuscation. And one of them started by saying, of course, it would be trivial to do obfuscation if you had cryptography. But we don't want to use cryptographic methods. So this is where we started.
Do you still have the paper?
Why?
Russell,
Trivial.
do you still have the paper, Russell?
It's referenced, I believe it's referenced in the VGI, et cetera.
Okay, an interesting set, hopefully.
The margins were too narrow.
Yeah, it's too simple, it's too difficult even to discuss probably. This is why, you know, we're almost like, we are 15 years later and we just 50, like apparently it was simple back then, so it took so much time to get it to it now, like it's the same kind of concept that you mentioned. So I hope it answers your question. So now I guess any other questions, complaints, concerns? I hope I satisfied all the previous complaints, so now we can actually talk about some of the results. So our results come in different flavors, and I'll try to mention the result of the flavor. So the first flavor is lower bounds from an IO, and what I started the question with. So the first set of results will show lower bounds from IO, which is, so the important things are perfect and secure against P/poly. So P/poly means non-uniform adversary. So if you have a perfect IO which is secure against non-uniform adversary, you get two lower bounds. I mean, you get two flavors of lower bounds. First, you get lower bounds from next exponential, non-deterministic exponential time, and if you scale it down, sort of, you get a lower bound for empty. So this is what's called fixed polynomial lower bounds. You don't get to show that NP is not in P/poly. It's like the name of the game, right? P/poly means that for every polynomial function, you cannot compute it. Here is you pick it for every k, you find a different language. That's the difference between those two types of lower bounds. So the first flavor, and then what happens if you if you're SEM and you want to compromise security, if you want to compromise perfectness, so you can go up to a certain point to get an imperfect. You don't have to, like, if you go to c equals 5, you don't get it, but you can actually go pretty low and say that, well, if it's pretty low, then even if it's an imperfect, you don't recover the same lower bounds, you get lower bounds for the class MA, which is the randomized version of that. So a few remarks on this result to put it in the context. So to the best of our knowledge, our means Russell, Valentin, and myself in this context. To the best of our knowledge, this is the first time when you can get low bounds of the existence of an IO. If you know otherwise, then the three of us, please come talk to one of us to discuss that, because it will be interesting to see. I couldn't find anything, so this is one thing I want to say. Another thing is that sort of, you know, we have those lower bounds. Let's try to compare them with what's out there. So unconditionally, the best unconditional thing we have is a lower bound for MAX, which is the exponential version for MA, and MA/1. So I don't know, it maybe looks ridiculous. Yes, this looks very, very similar, except for this one annoying bit of advice. Now, everyone here, I know how much you think about it, you wouldn't believe how much effort has been spent in the past 15 years trying to get rid of this one bit of advice. You wouldn't believe. So, for once, you can think about I/O as a bit saver, advice bit saver. It allows you to save this one extra annoying bit of advice because you can get the lower bound without that. Yes, Russell?
Just why it's a big gap is really, we shouldn't be actually saying we have a lower bound for MA1. What we have is a lower bound for promise MA1.
Which translates to that.
That's right. So if you get the advice wrong, it's not only not hard, it's not necessarily an MA.
Yes.
So, and so that's why, like, also BPP one is very different from BPP because it's closer to promise BPP. All classes that are kind of syntactic.
Right.
Syntactic?
Semantic.
Semantic, sorry.
Yes.
Try that, reverse it.
As per Russell's comment, it is actually the case that this is potentially a bound against promise BPP, and now if you have I/O, you can forget about the promise and get it for that. So if you don't like to save bits of advice, you can save yourself the promise.
Yeah.
Marco?
Is MAX non-NP poly really better than ZPX to the MCSP non-NP poly?
Is that really better? Well, MAX is a subclass, okay, let's start on the low end regime. MA is a syntactic subclass of BPP to the NP.
To the NP?
Yes,
Right.
you're asking about, but what you're asking about is, we don't know, that's one of the open questions.
Oh.
If you solve the hypothesis of the conjecture that I mentioned a few slides back, you get what we want. We don't know. We don't know whether MA is in ZPP to the MCSP. We don't know that.
Okay.
Again, if you know how to do it, it will resolve the conjecture, but we know, again, MA is in ZPP to the NP, we know that, we don't know how to replace the NP oracle with an MCSP oracle in that case. What we do have, and this is maybe what you're asking about, we do have lower bounds for ZPX to the MCSP, we do have that.
Yeah, so that's, I don't know, it looks better to me, because MCSP is mentioned classic. Sorry.
You can
I guess
actually
it
get,
depends on whether you believe MCSP is NP complete or not.
Okay, yes, yeah.
so maybe to sort of connect the dots here, you can actually show lower bound for that intersection. So by intersection, I mean, that's why we don't put it on slides, but since you asked, for you, Marco, and I think Valentin did it in the paper, you put everything together in one line in the final theorem. You can show it's MAX intersect ZPP to like the class MAX intersect ZPX to the MCSP, that thing, that monster, you can show lower bound for that unconditionally. And conditionally, as Valentin did, right, this was like a very complicated thing to write, so thank you for doing it. But anyway, it was written as, if you open the paper, NAX intersect ZPX to the NCSP. This is the full result that we have here. And to add an insult to an injury, it's actually NAX intersect co-NAX intersect ZPP to the NCSP. But this is not something to write in this slide, right?
Thank you for saying, like, I feel a lot better.
I'm glad, very glad. I'm very glad that you're feeling better, Mark. So is there anyone else I can make feel better? So let me just sort of based on the discussion here, maybe summarize and say that we as a community now, not the three of us, we as a community believe that those kinds of lower bounds, all the lower bounds, in fact on the slide should hold unconditionally, without any premises, without any assumptions, but they're like light years away of making any progress towards that. So Ryan Williams actually has a very nice survey. So it was written more than 10 years ago, and the sad part is that the sad thing, it's not that Ryan is not a good writer, Ryan is a great writer. The sad part is that it's still relevant 10 years from now. The problems that Ryan identified in that paper are still there. So this is why basically we're still far away from showing any of those things unconditionally, including removing this bit of advice for community promise. Questions, concerns, complaints? So
are there any barriers for that, like removing one bit of advice?
What's the question, Rich?
Oh, sorry, are there any barriers for that?
Barrier. So there is a suggestion. It's more like a suggestion. So one of the suggestions was made by, well, in the community we have, I don't know, not to offend anyone, we have two Rahuls. So one Rahul is here, the other one is not here. So I don't want to say the other Rahul, but I say Rahul Santanam. In his paper, when he proved this Santanam 09, when he proved this bound, suggested that this kind of, it predated the paper, and they suggested that there's a third bound, and 3 years after that, we had a paper of algebrization by Avi and Scott. So basically, apparently there's an algebrization bound, and we don't know, to overcome that, we might be able to get rid of this advice, but like this the whole thing is the algebra. Basically. This is, I mean, one explanation that I have. Another explanation is basically what Russell said is, dealing with those kind of semantic classes, it's a pain. Like, we don't know how to deal with semantic classes, period. We don't have hierarchy theorems, we don't have anything for that. So this is one of the manifestations of this dealing with semantic classes. I guess. Questions? Marco?
Wait, but Shuichi, isn't there a boundary relativization barrier to getting rid of the problem summary?
Which barrier?
I-
Which barrier, Marco?
The proof, if I remember right, Rahul's, MA1 is not in size under the K. That's piece-based relativizing. That's from this bounded relativization paper, Shuichi, Zenshan, Han Lin. And so if you were able to do,
So
if you could do it, I don't know, maybe it's not about the advice, maybe it's about almost everywhere versus. Sorry.
So, I mean, there are probably barriers, and there's more than one barrier, but as a matter of fact, 2009 stock version came in 2007, we're like almost 20 years past that, and again, you know, this is a wasted effort or not. There were so many attempts using PCP theorems, using all kinds of, how do you call it, Marco? Complexity jump or complexity, what was the term you used?
Complexity jump for it.
Complexity jump. Complexity jump drawer, or whichever term you may come up with. People used so many tried to use so many heavy cannons and guns and whatnot to remove it, and it's still there. But IO allows, again, you can think about IO allows you to save all of this arsenal that was used for 20 years.
Can you get almost everywhere lower against memory?
Here?
Yeah.
I think you can get the IO here, yes. I think in all of them you can get IO.
I will mean infinite.
Infinitely often.
Okay.
The small IO, like the big IO is this, there's a small IO. More questions? Good. So this is the first flavor. The second flavor is kind of what the title suggests, how IO empowers MCSP, right? So here we're actually changing the assumption a little bit. So now we're assuming a perfect computational secure IO. So computational secure is secure against, you know, uniform algorithm. So we get something which I find rather amusing, and the following. So if MCSP is in BPP, then NP is in ZPP. So I remember first Valentin talked about it's like a very nice thing. Like think about what's going on here. You take one problem in a class, and in BPP, not only it pulls all the class down, it pulls all the class below its own weight. So ZPP is believed to be, it's a subclass of BPP. This is, I think, quite amusing, and that's of course a known name. So now, one consequence of this result is we get a separation of complexity classes. From complexity classes, we get to separate ZPX from VPP. That's the exponent partial version of VPP. Okay, so a few remarks about that. So let me talk about this particular thing here. Why is it even interesting? Who cares about those two weird classes? Well, so as we discussed, as Russell mentioned, when it comes to dealing with semantic classes, we are in trouble. We don't have hierarchy theorems. We cannot do much. But if all you want in your life is to separate ZPX from ZPP, basically the exponential gap, you can actually do that. So that's it. it's not that easy when you want to turn out the heat a little bit, and if you want to separate next from BPP or even so X to the empty from BPP. So just to be clear, this is a superclass of members. X is an empty oracle. So we have no idea how to do that. And as I've said, Ryan has a great paper about that. And all the problems for 2014 are still there. Unfortunately, we did not make any progress. So that is that. And now to make it even more interesting, if you want to separate ZPX from BPP, we really have no clue. ZPX is a subclass of next. So again, separating ZPX from BPP would imply separating next from BPP, which we have no idea how to do. So here we're even more sort of clueless. So at the same time, one of the results that if you have IO, you actually get to separate these two complexity classes. Questions, concerns, complaints? Now, before you ask the question, what seems to be the barrier here? So, one sort of, suggestion or one possible barrier is the old relativization barrier, which is the fact that you can actually construct an oracle when those three things, BPP, NX, like all those things here are actually going to be equal. So it has to be non-relativizable somehow. So, I mean, if you kind of flip it here, one of the conclusions you can get is that IO doesn't exist relative to that oracle. Now, before you say anything, yes, that's not the best way to do it. You can probably take one of the, you can take, I don't know, a Besselian oracle and get it in the same way, but I think it's an interesting way to connect it. And you can kind of think about connecting this whole thing with this random oracle hypothesis, right? So, a question, I don't know, Russell, maybe you know the answer to that. Does IO exist relative to a random oracle?
No, yes.
Or maybe maybe your results about the MCSP.
Well, no, yeah, so actually, okay, so
Maybe your
what we can
results.
say is that if P equals NP in real life, it does not exist relative to a random oracle, because that would imply public key encryption. So it's complicated.
So
I mean, of course, it could exist relative to a random oracle, if it exists without a random oracle, and the random oracle doesn't help you break anything. I mean, the random oracle usually doesn't help you break anything. That's really like.
So that's, I think, another way to think about it. It's
So we won't. We're not going to answer that question today.
so that's good. We have something to think about. We have until tomorrow anyway. So that's another way to connect IO with this line of work. And I guess the final flavor. How much time do I have? Okay, good. The final flavor is sort of how MCSP empowers IO. And this takes us back to this broader definition of security that I talked about, right? So again, when you talk about a definition of security, it's usually in the literature one of these two extreme cases. Either computational security, BPP, non-uniform security, P/poly here, or all the way in, which is statistical security, which is Sam seems to be a like a fan of that kind of thing. So as it turns out, one of the applications or one of the results that we get is that you don't actually have to be all the way in to be all the way in. What do we mean by that? So IO is statistically secure if and only if it's secure against a much smaller class of algorithms, which is BPP to the MCSP. So again, if you think about it, you are secure against exponential time, exponential space, double exponential space, pick your favorite, as long as you're secure enough this small animal called BPP to the MCSP, something which is in the second level or the third level of the polynomial hierarchy. So you don't have to go to that length to be secure against those things, and in particular, what you said, this one-way thing will, it also be secure against that for that same reason. So This is, by the way, let me just say, it's not just true for I/O, it's basically true for any distributions. If you take any distributions, any two distributions are statistically secure if and only if they're secure against VPP to the MCSP. Kind of scale down every statistical thing out there to that level.
The distribution is like, they are evenly separable.
Even any distribution.
Any distribution, like that's how to describe the distribution then.
If you wait for, I don't know, 4 or 5 more slides, I'll actually talk about that if I have time, if not, I'll talk about offline. So yes, it's true for any, like, obviously, if you want to talk about security, you have to have asymptotics, right? It's not like one, it's not just one thing, so you have to have a, a sequence. Yes, Russell?
Is this also like, can you replace the VPP to the MSDSP by statistical zero knowledge? Because then you're kind of like this, you look at like the two, distributions and you have to say whether, how much they overlap.
But statistical, the thing about statistical zero knowledge is that's sort of like, okay, I think we talked about it when we were writing the paper. Statistical zero knowledge is, okay, you want the distributions to be, when you have the transcript and that you want to be statistically close, right? Instead, you can strike the word statistically and say you want to be close by that distinguisher. I know this was your question, but any place, if any time you have statistically whatever distributions or everything, you have statistical, you can just strike it out and replace it by that. What is answer your question, Russ?
I'm not sure.
Okay, no. We can ask again. So, what is one of the applications that we get is, we'll see that, but another application we get is the following. We also get that flavor of completeness under imperfect I/O. So we already had this for perfect I/O, now we can do it for imperfect I/O. That flavor of completeness, basically VPP, MCSPs and VPP, if and only if they fall empty class of VPP. So this is another actually outcome of that result. So let me again make some remarks, put it in the context. All what I've talked about, all the things I talked about, they're all true, but it's a bit of exaggeration. What do I mean by that? So in order to get all of those lower bounds, you don't actually need an I/O for all circuit classes. No, it's enough to get an I/O, which is good for some smaller circuit classes. Specifically, you want an I/O for a class for which the equivalence problem is going to be hard. So what's the equivalence problem? I give you two circuits and I ask you, do they compute the same function? That's the equivalence problem. So this is going to be hard for 3CNFs or monotone depth-3 formulas or read-wise. So this is, I think, an interesting thing that it's enough to be able to obfuscate monotone circuits of depth-3 or monotone formulas of depth-3. If you can obfuscate them, you already get all these results. Just as easy as before. And now, sort of on the positive side, what happens in the literature? You usually start, if you want to get it all the way to P-poly, you don't start with P-poly, you start with something like MC1 formulas, and then you bootstrap it all the way. So if you can look at this, these are much smaller objects. So 3CNF is a much smaller object than MC1. Right, so you already run into the slower bounds, even in a much earlier level. Something that I've never said in any of the presentation, but I'm going to say it now because it's actually something that was observed recently. All these results, the lower bounds, they don't just follow from I/O, they follow from a simple logic that Ellie was talking about, witness encryption. So you can get the lower bounds with I haven't written it down, but you can get the lower bound, assuming you have the witness encryption the way that Haley described. I'm not going to do it. That's the benefit of being one of the last speakers, but you can get that as well. Questions, concerns, complaints? So let me maybe as a use case try to run through one particular example of how we put lower bounds given what we have. Give you an idea, a taste of the technique. So before that, questions, concerns, complaints. So the starting point of this low line work, goes back to about 20 years ago, a result of Goldwasser and Lovelock. They pretty much tried to argue against, they argued against the existence of statistically secure IO, so your allies, which pretty much said, okay, suppose you have statistically secure IO, what happens? So the argument was if you had such a thing, then the polynomial hierarchy collapses all the way to AM. Which is something unlikely, so essentially from that point on, everyone who said something about statistically secure IO, everybody stopped listening because it would be like saying if pigs could fly, if elephants could swim, etc., etc. Right? So, well, elephants could fly then. Elephant could fly, okay. It would be easier, like Dumbo. So from that point of view, there is not much point of saying, if I have statistical IO that something happened, that's not interesting. So it kind of stopped. And indeed, in practice or in all the work in cryptography work, people do not assume statistically secure IO, they assume IO which is secure, like computational secure IO. But this is kind of when one thing ended and we kind of started, because I would like to spin this over to see how we get a lower bound. Sorry. The first thing to observe that, to kind of recall that we know for the polynomial hierarchy that we do have circuit lower bounds. That's a nice demonetization exercise. You can pretty much diagonalize against all circuits of size until decay. So we're going to run through a sequence of, I know it's a late hour in the day, but we're going to run through a sequence of substitution and rewriting exercises. So what do we have here? If statistically secure IO imply the polynomial hierarchy collapses to AM. What happens when the hierarchy collapses to AM? AM inherits everything, including those half languages. So what's the conclusion? The conclusion is that AM has lower bounds of that form. So again, that's not interesting because the premise is still if pigs could fly or elephants could fly, as per Russell's suggestion. Okay, so how do we make it somewhat more interesting? To make it slightly more interesting, we're going to use that result that we have, which equates statistical security with security against a smaller subclass of individual MCSQ. So again, this is statistical, this is statistical, this is that, so I'm going to swap this for that. What I'm going to get, if we have IO which is secure against the MCSP, then we get lower bounds for that. But this is essentially playing the semantics, right? This is just making something look nicer because we know the truth. This is equivalent to that. So this might impress some, but still, let's say it's like if pigs could fly in some concealed way, right?
Like an airplane?
If pigs could fly, be a pilot on an airplane, or something like that. So when does it become more interesting? So this is what we have so far, right? So let's see how we actually get it. So to get to the result, when we get lower bound under sort of, an assumption that we're willing to accept and not an assignment, the pigs could fly, remember what our result was. So our result for the imperfect case, if we have an imperfect IO secure against P/pool, again, this is something that we are willing to accept, and this is actually used, this assumption used in many cryptographic papers, that we get lower bounds for IO. Okay, so how do we get from here to here, basically? How do we get? So this is another one of those rewriting exercise. So if you know a shell game, when you have you put a ball under a pen and you have to find out where the ball is, right? It's just kind of, we're going to do the same thing. We're going to try to follow the ball, and you need to make sure that I'm not cheating and hiding the ball somewhere else. So that's what we have, right? That's what we have so far. So let's see how it works. So the lower bound that we get is using the traditional win-win argument or the traditional two-pronged approach, as Eric Arender likes to call it. So remember what the state is, and this is how the proof goes. We have two cases, and we're going to get a win in each case. And the condition that we're going to look at is where do we live in terms of IO? Remember, IO of Piscatopia, it's an island which is split into two parts. One part is algorithmica, the other part is cryptomania. So we're going to see that whichever part of the island we're at, we're going to get what we want. And interestingly, This distinction is made by looking at the relevant complexity of MCSP. So what do I mean by that? So first case, this case represents cryptomania. MCSP is not complete with body. We don't have an efficient non-uniform solution for MCSP. So this is like what we expect in cryptomania to happen, but let's point we're done. Why? Because MCSP is an NP, which is an AM. So here is this one problem in AM, which doesn't have small circuits. Now, what happens if we found ourselves on the other side of the island? What happens in algorithmica? So this will be this rewriting exercise that we want to do. So on the other side of the island, MCSP is in P/poly. So basically we don't have one with concretes actually. So what happens then? So let's just follow the path. Okay, a rewriting exercise with the participation of the audience. If MCSP is in P/poly, by using Adelman's argument, you get that BPP to the MCSP is in P/poly. And now, let's just try to do, I know that none of us was a literature major in school, but I think we can do it. So let's read what we have. So this is the condition of the theorem. We have an imperfect IO secure against P/poly, right? That's what we have. And what else do we have? We have that BPP to the MCSP is in P/poly. So it's secure against this big class of algorithms, and this is a subclass of that class. What's the conclusion? We are secure against BPP to the MCSP. Agree with that? This is just the writing exercise. Again, you're secure against this, and this is a part of this, so you're secure against that. Agree with that? But now, again, watch the ball. Where did we see this before? What happens if we secure against this? Then we get the low bound. So that's the result. So now we don't know which side of the island we're at. If you ask, actually, I always wanted to ask Russell, where do you think, which world do you think we live in? But for that matter, for right now, it may not matter because no matter where we are, we're in cryptomania or algorithmica, each one of those cases give us lower bound or MA. So if you combine them, this is how you recover that result. Questions, concerns, complaints? Now, if you want to go to the perfect case and get an NP, you have to use a different starting point. You have to use a different result that says if you have perfect IO secure against this class, then the hierarchy collapses to NP and not to ADA. That is how you get the next level of that. Questions, concerns, complaints? How much time? So, I guess in 2 minutes, I can kind of try to sketch at least what's sort of behind this whole thing. And this is the question that some of you ask here about distinguishability. So, like, let me take you back to maybe a simple problem of distinguishing two distributions. So we have two samples represented by circuits. And we want to find the best possible distinguishing. It's a distinguishing game, right? You're given a sample from one, a sample from another one, you want to figure out which one it is. So if all I care about is finding the best possible distinguisher, we know the answer to this question. That is, like you're saying, this is the maximum likelihood distinguisher. Basically, you look at the sample and see which circuit attributes more mass to that. You can do that, and this gives rise to this notion of statistical distance, exactly how you get the statistical distance. But there is one problem instead. What's the problem? It's very, very, very inefficient. So how can you do it? So, well, if you just naively try to do it, if you want to count the math, that's a sharp P question, so you can do it and give the sharp P. That's high enough in the sky. Now, you can relax that because many times you just want an approximate. So you can approximate it by sampling using MCMC or that kind of the machinery. You can approximate it and give it to the NP. That's still higher in the sky. I mean, that's better than P to the sharp, of course, but that's still higher in the sky. So one of the main contributions that we achieve is we show how to essentially do it in BPP to the MCSP. So instead of NP here, we get an MCSP or so that's essentially what we get. We get a distinguisher that basically is the following guarantee. So it gives you distance, but you cannot do better than statistical, of course, but the most important thing is that you're not doing too much off, you're doing closer to that. So let me just mention, so this actually works. The way that we need it is, if you do like the works of Goldright and L, you can actually do it in a uniform way, but it will be in the wrong order. So for every ensemble, there is a distinguisher. The main thing that we have to do is to switch the quantifiers. We have a universal distinguisher. So to answer your question, Luigi, this is a universal. Basically, for any ensemble, for any distributions, you have this algorithm, you to the MCSP that will recover the distance up to an epsilon, right? So for any.
Well, I was thinking like, I mean, they are at least samplable by circuits.
Again, if this is the previous works can do that. If you want to use the word of Goldright, you can do that. But in our case, they don't have to be samplable by anything.
I mean, it's like you have given two circuits, zero and one.
How else? Okay, how else do you get access to the circuits are non-uniform. That's the point. How else? Okay, how else do you get access to the distribution?
Oh, well, never.
No, I mean it's not a matter of uniformity. It's a matter of here two concrete circuits. Okay, how else are you going to get access to the distribution? That's not it's not a part of an ensemble, right? Does it make sense? So let me just summarize. So we had a line of work where they kind of try to get an evidentiary pass. We're trying to take every result that has an NP oracle and replace it with an MCSP oracle, similar to what Marco was trying to do earlier, and see that it holds. So here's another example. This is the example of we could do it. We could do the best. We could approximate a good distinguisher with BPP to the NP. What we did, we can actually now approximate it with BPP to the MC. There's another example that perhaps MCSP is NP complete, NP hard. Sorry, Russell, NP hard, but under the more broader notion. So with that, let me finish and talk about what we have. So we have those flavors of MCSP empowering. This and that, by the way, that's a comment that when we submitted this paper to the conference, it was a different title, and then someone suggested that we change the title. It was what was the original title? Synergy or mutual empowerment. Anyway, so a reviewer that might be in the audience or not suggested that we should change the title. So thank you for the suggestion if you're here. Nonetheless, we've seen examples of how they empower IO and MCSP and empower each other. So there are several questions. For example, can we get lower bounds when we have non-uniform security? Can we get lower bounds on uniform security? That's one question. Another question, which is again going back to the hardness, can we prove the hardness of MCSP? Assume what you want. Assume that you have the best possible IO. Assume that you have take the most liberal notion of completeness. Can you prove anything about sort of a formal statement of hardness? Can you do that? And the other question, which is kind of in the spirit of what we discussed in this workshop, is can we close the gap between hardness of MCSP and existence of IO, the existence of one functions with IOs? So my time is up. So thank you very much. No, not enough. I think I will you more.
Okay, after each talk, there will be a break and there will be more grading. Thank you so much. Thank you for making our beautiful at home by connecting the ends of the